Binary heaps. Right. Now, what is a binary heap? A binary heap is a kind of binary search tree where the only value that we're really concerned with is the value at the very top of the tree. Now, that being said, notice that I said binary heap is a kind of binary tree, not a kind of binary search tree. Now, what do I mean by that? Well, in a binary search tree, like we discussed previously, they're ordered from left to right. The left child must be lesser than the parent, and the right child must be greater than the parent, meaning the right child will always be greater than the left child. In the binary tree, the nodes aren't ordered at all. There is no rule as far as ordering is concerned. The only rule is that the parent can have no more than two children. A binary heap is somewhere in between the two, which is why we call it weakly ordered. The only rule as far as binary heaps are concerned is that the parent must be less than the two children. Right? That's if you're doing a minimum heap. You could also do a maximum heap where the parent must be greater than the children. In either case, there is no relationship between the siblings. There's no rule that says the left child must be greater than the right child or vice versa. The only relationship is from parent to child. Now, another property that binary heaps have is that they must be complete. And what I mean by that is the tree must be completely filled from top to bottom, from left to right, with the exception of the last row. And even if the last row isn't full, it still needs to at least start from the very far left and be completely filled from left to right. What that means is a tree like this would be illegal, invalid, because again, the bottom row must start at the far left. Also, a tree like this would be illegal because there cannot be any gaps in the bottom row. The row must be filled from left to right. So, if your bottom row is not going to be completely filled, at the very least, it must start at the very far left and must be completely filled from left to right. Now, on to the operations. Suppose this is my heap, and as you can see, this is a maximum heap because each parent is greater than its two children. Now, suppose I want to insert the number 99 into the heap. The first step for a heap insertion is to make that node the last node in the heap. So that's where I put 99. Now, that being said, it's possible after doing this that my new node could be violating the heap ordering rule. It's possible that the node I inserted could be greater than its parent. So what I'm going to do is trickle up. And what I mean by that is I'm going to compare this new node to its parent. Since 99 is greater than 69, I'm going to swap it. And now I'm going to compare 99 to its new parent. Since 99 is greater than 78, I'll swap again. And now I'm going to compare 99 to its new parent. Since 99 is smaller, no violation has occurred, thus the insertion is done. Now, the next important operation in a binary heap is remove max, or if you were working with a minimum heap, it would be remove min. In either case, you might be wondering, what about the remove operation to remove some arbitrary value in the heap? Binary heaps do not do that. There is no remove 85 or remove 78. There's only remove max and remove min because once again, in a heap, you're only concerned with the value at the top, which in this case is always the maximum value. So how do we remove the maximum value in a tree, in a heap? What we're going to do is we're going to take the last node and we're going to swap it with the root. Then we're going to remove the last node. Right? We do this because it's very simple. It's a lot simpler to simply remove the last node than it is to remove any other node in the heap. Now, that being said, after doing this swap process, it's possible that 69, the former last node, could be violating our heap ordering process. So what we're going to do is trickle down this time. And what that means is I'm going to compare 69 to its children. But which child? As you can see, there's a violation on both sides of 69. It's smaller than both of its children. So which child should I swap it with? Well, let's say, for argument's sake, that we assume it doesn't matter which node we swap it with. Let's say we choose to swap it with 94. All right, well, when we do that, as you can see, we still haven't solved the problem at the root because now 94 is smaller then it's the right child, 99. So, rather than arbitrarily pick who we swap 69 with, whenever you have a violation on both sides of the parent, swap it with the larger of the two children. That ensures that after the swap is done, that there won't be another violation still occurring at the root. All right, so now that that first swap is done, now we're going to compare 69 to its new two children. Since in this case a violation only occurs on the left side, we only consider the left side, and that's who we swap 69 with. Then we compare 69 to its new child. We see that 69 is larger, thus the trickle down process is finished and remove maxed is done. And that completes our discussion on binary heaps.